Hello and welcome to the Godless Family Webcast. I'm your host, Aubrey Adrianson, and with me tonight is my co-host, Amanda Hayes. Say hello, Amanda.
Hi, everyone.
And with us tonight is Daniel Bacheldor. He is an astrophysicist and professor at the Florida Institute of Technology. Say hello, Dan.
Hi, everyone.
And tonight we're going to be talking about the Big Bang, which happens to be within Dan's field of expertise. So first we're going to have Dan introduce himself and tell us anything he wants about himself.
Okay, sounds good. So I have a bachelor's degree in astronomy from the University of Hertfordshire. I got that in 2001. And then I spent 3 years doing a PhD in astrophysics, looking at black holes at the centers of galaxies. And then I moved to the United States in 2005 to Rochester Institute of Technology, and I spent 6 years there doing research using basically the Hubble Space Telescope and other ground-based telescopes to carry on what I had been doing in my PhD. And then I started doing some teaching and getting all of the experience I needed to become a faculty member. And in 2010, I was hired as a faculty member at Florida Institute of Technology. So right now, I still work with the Hubble Space Telescope, and we're also developing some other instrumentation that's going to help us hopefully make an image of a planet around another star, an Earth-like planet around another star in the next 20 years or so. So that's the kind of stuff that I've been doing. And when I'm teaching, I teach everything from introductory physics, so that's kind of how things move around, what we call Newtonian mechanics, and then all the way up to astrophysics 2, which is the physics of galaxies and the universe and cosmology and the early universe and the beginning of the universe and stuff like that. Yeah.
All right. Great. Thank you, Dan.
Okay.
So I would love to just dip into our questions and get right into our topic. And the first item is for you just to explain the theory itself. So what is the Big Bang Theory?
So the Big Bang Theory is the best model that we have to explain how the universe evolved just after it began. So the theory itself doesn't deal with the actual mechanism that began the universe, but we can explain with the Big Bang Theory everything from about 1/1000th of a second after the event began. And we have really good observational evidence to back up this theory. So you frequently hear people talking about theories as in the theory of evolution, things being just a theory, but the Big Bang Theory is the best model that we have, so we consider it to be a fact, right? So this is what happened, and we can prove it. And there is no need to invoke any kind of supernatural explanation. We actually can explain it all the way back to 1/1000th of a second after the event happened. Before then, there are more vague models to explain what happened, but there is no need to invoke any kind of supernatural explanation for the way the universe evolved from 1/1000th of a second after the event actually occurred. So after that, we can explain how the universe cooled, expanded, how the first stars evolved, how the first galaxies came about, and then how the first planets formed, and we can explain everything with a few minor details here and there, everything all the way up to the current time.
Great. Is there anything about the theory, any basics that you want to cover, or you want to dip right into evidence?
Well, the basics actually involve the evidence, right? So
okay.
It's kind of a nice history story, and it's a very good demonstration of how we use the scientific method. So one of the reasons the theory is so strong is that there are independent sources of evidence that made predictions that then were later shown through observation to be true. All right, so this is one of the beauties of the scientific method, is that it's predictive. So you can explain an observation that then has a consequence, and then you can go and test to see if that the consequence that you came up with is actually true. So the first piece of evidence that we had for the universe having an origin in the past is actually the observation of how galaxies appear to be moving away from one another. So if we look at all of the galaxies in the universe, if we look at a close galaxy, it appears to be moving away from us with a particular speed. And if we look at a galaxy that's even further away, that galaxy is moving away from us at an even faster speed. So that observation is very, very strong, and every time we look at galaxies that are far away, we see that they're moving away from us. And this relationship is known as Hubble's law. So we can actually make a relationship between how far a galaxy is away and how fast it is moving away from us. Okay? So all you need to do from that observation is turn it on its head and say, if all the galaxies are moving away from us now, what were they doing in the past? So in the past, they had to be closer together, and at one point, they had to be all in the same position based on that. So Hubble's law comes up with a number, and that number can actually tell us when the event occurred. So if you plot, well, if you have a relationship between a speed, which is a distance as a function of time, so let's say meters per second or kilometers per second, and you plot that against another distance, the distance to the galaxy, then the only unit we have left is time, which tells us exactly how long the universe has been expanding for. So Hubble's law both tells us that the universe had a beginning, and then the Hubble's constant tells us exactly when that beginning occurred. So there's some number, you do a simple unit conversion, you don't need any advanced mathematics to show this. Once you know Hubble's constant, you just do a simple unit conversion from kilometers per second to megaparsec to time, to seconds. And this is how we come up with the number 13.8 billion years. So when you look at the universe, you see all of these galaxies are spread out everywhere. So all of the light and the energy and the heat and everything is spread out throughout the current volume of the universe. So if the universe was smaller in the past, well, not if, the universe was smaller in the past, that means all of that energy is compacted into a smaller and smaller volume. So that means at some point in the past, the universe was so dense that light couldn't actually pass through the universe. And as the universe expanded, at some point light was able to pass through the universe itself. So this gives us a prediction. It tells us that at some point in the past we will be able to see the leftover fireball from the Big Bang. So that's one of the predictions, and this was a prediction that was made and then later verified through observation.
Okay.
So that's one major piece of evidence for the Big Bang Theory. Independently of that, we can look at the ratio of hydrogen and helium in the universe. So as we look through the universe, we can actually determine how much hydrogen and helium there is and look at the ratio between those two elements. So hydrogen is the nasty one. Hydrogen is the reason that one of the reasons the Hindenburg, one of the reasons you don't use large airships anymore, because it's highly volatile, very flammable. And helium is the next light one, but it's inert, right? But anyway, so the ratio of hydrogen to helium in the universe is approximately 3 to 1. Now, the only way that you can actually create helium is from hydrogen. You basically, in some way, get 4 hydrogen atoms, stick them together, and you can create helium. The only way you can do that is in a very hot, dense part of the universe. Now, we know that this happens at the cores of stars. So our star, our sun, is processing hydrogen into helium. And when it runs out of hydrogen, that's when we know that the sun is going to end its life. But stars aren't efficient enough at converting hydrogen into helium to reproduce the ratio that we see between hydrogen and helium. So because of the large ratio of 3 to 1 between hydrogen and helium, we know that in the past, the entire universe had to be at some temperature where you could fuse hydrogen into helium. So that also gives us independent evidence, independent from Hubble's law, that the universe had a hot, dense past. And we can actually calculate the temperature of the universe needed to produce the hydrogen and helium. And once again, we get to the point where we need a universe that is so hot that photons, light, can't pass through the universe. And as the universe would have expanded, there would be a point where photons could travel through the universe, and we'd be able to see that leftover fireball. And so It was actually accidentally discovered, the fireball, back in the 60s. And there's now a national monument in New Jersey. So hooray for New Jersey, you have a national monument. It's called the Bell Horn Antenna. And it was a device that was being used to communicate with some of the early satellites. So it was listening for microwave emissions from satellites. And when they turned it on, they found that there was a background noise of microwaves coming from wherever they pointed that antenna. And it turned out that was the actual signal left over from the hot, dense event that we describe now as the Big Bang.
Awesome. Anything else?
So the predictive power of the Big Bang is one of the best models that we've actually ever fitted to what's known as the black body spectrum. So when something's hot, it emits light at a very particular wavelength, right? So for example, when you look at a flame, you notice the base of the flame is blue because that's the hottest part, and the top of the flame is orange because it's cooler. Well, we can actually make that into a nice plot, and we can actually plot, we can fit a temperature model to that data to actually determine exactly what temperature the flame is, or what particular temperature that part of the flame is. We can actually do this with the signal from the Big Bang, and this is the best model that we've ever had for fitting the thermal emission, how hot the universe was in the past. So this is really, really well known. There have been satellites actually put up. There's been three satellites, major satellites, COBE, WMAP, and Planck are their names. And they're acronyms for various things, but all they're doing is they're looking for the signal from the fireball left over at from the Big Bang. And each instrument has been more expensive and more accurate. So our models for the Big Bang have been getting better and better and better and better, to the point where we know the age of the universe now to 5 or 6 significant figures. So we can say that it's 13.7 XX years old based on the data that have come from these satellites.
Wow.
So this is actually unusual in astronomy, to be able to get such a precise measurement. One of the cool things about astronomy is that it's not a typical science, in that you can't manipulate the system that you're testing. All you can do is basically stare at whatever you're observing, right? So you can't. It's not like a biologist, where a biologist can pick up a bit of water and put it under a microscope and filter out bits and find what's in it and warm something up and cool something down. All we can do in astronomy is stare, which means that we're not very good at doing things like measuring the distance to something, right? Because you can't go out and just take a tape measure and go, right, it's X number of meters away, right? So normally we're very imprecise in astronomy. We like to know the difference between 1, 10, 100, 1,000. Right. But with the evidence that we have for the Big Bang, we actually know that it's very, very precisely modeled. So this is one of the cool things about the Big Bang theory, is that it's kind of an unusual event in astronomy to have such a strong theory. Yeah.
Okay. So let me ask this question. If the universe was so dense in the past, then why wasn't it a black hole?
Okay, so the thing that's happening with the universe is that it itself is expanding, right? So when you think about a planet or a star, you're thinking about a three-dimensional object that you are observing from outside of that object, right? So when we look at the moon, we see the moon, and we are observing it from outside of the moon's frame of reference. Right? So a black hole, for example, we always observe them from outside of the black hole, which means that in the universe, we're actually inside the universe, right? Which makes it a very different environment to what we are normally experiencing. So one of the things that the universe has been doing is expanding very, 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 very rapidly. So one of the reasons the universe just didn't collapse back down into a black hole, and that was the end of the universe, is that there was this massive, massive period of expansion where the universe expanded so fast that all of the matter basically got to a very such a low density that we weren't in the regime that you would normally describe as a black hole. So yeah, it's very interesting, and it's very conceptually quite difficult to appreciate, because in everyday life we're happy going up, down, left and right, backwards and forwards. But we're actually inside a universe that has a geometry that is in a higher dimension to what we're normally experiencing. So the normal analogy is to actually put yourself in the boots of a two-dimensional object living on a surface of a sphere. All right. So imagine we're an ant on the surface of the Earth. Right. We can't go up or down. So we are trying to describe the geometry of the Earth from the viewpoint of an ant walking around on the surface of the Earth. That's actually very difficult to do. So an ant doesn't know that the Earth isn't flat, right? Because they can't make the measurement to show that it's actually spherical. And that's the type of analogy that we use to describe the geometry of the universe. We're three-dimensional beings existing in this four-dimensional construct known as the universe. So as it's expanding, it's very difficult for us to conceptually put that back into the type of things that we are used to understanding.
Mm-hmm. Okay.
Yeah.
Great. Amanda, anything?
Yeah, I have a very rudimentary knowledge of the Big Bang, and so when my son asks me questions about it, I have a hard time answering. So I guess just to kind of go back to the basics, my first question would be if you have like some sort of kind of a simple explanation about the process of the Big Bang. Yeah, that's my question.
Okay, sure. So,
like, how, you know what I mean? What happens step by step? You know what I mean? Does that make sense?
Okay, so let's start off by making another analogy, right? Let's consider what happens to water as it changes temperature, right? So when water's really hot, it's in a gaseous form. It's got a very low density, right? And you can pass your hand through it, and it's not such a big deal. You can detect that it's there, right? Because it's kind of like this wispy stuff, and you can see that it's there. And that's kind of the way the universe is now, right? It's very spread out. And as you actually change the temperature of water, it's going to revert back into a different phase. It's going to go from gas to liquid, right? And when it goes to liquid, the way that light can actually pass through water compared to when it's in a gaseous form is very different, right? It's actually a lot more difficult for light to move through water than it is to move through air, right, or steam. So as we compress the universe, it actually goes back into a different state. Okay, so very, very early on in the universe, it was so dense that light couldn't actually pass through it. And
so I'm sorry, I was just going to say, so like it happened and then it was just like this big burning like ball of fire, is that what you're saying?
Well, it was very high temperature, yeah.
Okay.
Yeah, so it was. If you imagine an explosion, right? And you imagine the fireball from an explosion. At some point, it's orange, but as that fireball expands, suddenly it's no longer orange, and and then you can see through it.
Right. Okay.
Yeah, so it's kind of like that. But once again, going back to the fact that we're actually in that universe, that makes that observation slightly more tricky to conceptualize. Yeah.
So we're actually inside this explosion. I mean, it's not, it's still expanding, so I still kind of think of it as still kind of exploding.
Yeah.
Okay.
Yeah. So yeah, trying to make trying to describe the geometry of the universe, you have to do things very, very precisely. So one way we know that we live on the surface of a sphere, aside from the fact that we've gone to the moon and stuff like that, but consider yourself as an early Greek, right? So go back to early Greece and then try and prove that the Earth is spherical, right? Well, actually, just try and prove that the Earth is spherical right now, for example. So there's a couple of ways that you can do it, right? One of them is to walk in a very, very large triangle and then add up the angles within the triangle, and it will turn out that if you're living on the surface of a sphere, you'll add up the angles within that triangle and they'll come to more than 180 degrees. That means that you know that you are living on a surface of a sphere, on the surface of the sphere rather than the inside of the sphere. But the universe is a lot larger than the Earth, right? So to make that type of observation in the universe, you need an absolutely huge, huge, huge way of testing distance in the universe, right? You need to be able to tell how far away something is and then compare that to how far away you would think it was if the universe had a particular shape, right? So another way to compare this is if you're standing on the beach and you're looking at a ship moving away from you, at some point you're going to no longer see that ship because it's going to go over the horizon and you're going to see the mast disappear.
Mm-hmm.
All right? If the Earth was flat, you would just see that ship go away further and further and further away. It'd get smaller and smaller and smaller and smaller, but you'd still be able to see it as long as you've got good enough eyesight, right? So we can make those kind of tests in the universe by looking at really, really, really bright things. All right, and one of the brightest things in the universe is a supernova. So when a star explodes, we know that it has a particular brightness, or we think we know that it has a particular brightness. So if we look for these exploding stars in a universe that's flat, right, that star would have a particular brightness if the universe were flat. But if the universe were curved, then that star would have a slightly different brightness. It would be like the mast of the ship disappearing over the horizon. So we can wait and observe all of these supernovae going off and actually measure how bright we think they are, and then compare that to how bright they should be for a particular geometry of the universe. Yeah.
Okay.
So we can actually test that, and this is one of the observations that was made to show that the expansion of the universe is actually accelerating. It's actually getting faster and faster and faster. So one of the consequences of that is we're going towards a condition known as the heat death of the universe, right? It's where all of the energy is just going to be spread out to such a point that everything's just really, really cold. Yeah. So that's one of the consequences of that. So,
yeah, I was watching a video about that, scientists predict that at some point we're going to use up all of our hydrogen and helium and we're not going to have any stars and the universe is going to enter a dark phase.
Yeah, that's right. Yeah. But this is hundreds of billions.
Right. I'm not worried about it.
Me neither. No, there are more pressing matters right now. Yeah. Yeah. So you can make these arguments for like how is that a design? How is that an intelligent design? Right. I mean that's a really miserable end to the universe. Right. Counter to that, though, of course, there's sometimes the argument is made that we are existing in a particular time in the universe where we can actually show how the universe has evolved in the past. So we are actually living in a particularly privileged time. So if, for example, our sun formed in 10 billion years from now and the Earth formed 10 billion years from now, the universe would have expanded such that we couldn't actually make the observations that we are making now to show what the history of the universe was. So basically all of the ships that we see in the universe would have gone over that horizon, and we would no longer be able to see the evidence to show that the universe is actually had a hot, dense past. Yeah.
Okay. What about the universe contracting? Do you think that that's a possibility? I've heard some people talk about, well, if it expands, then it's going to contract.
Right. Yeah. So that was. One theory was that if the universe isn't expanding enough, then sooner or later gravity is going to take over and is going to collapse down in on itself. So based on what we know about the expansion of the universe and based on what we know about gravity, you can consider this, right? If you put your hands 1 meter apart, so about that much, and you ignored every other force that was happening on your hands, the space between your hands, because of the expansion of the universe, would actually increase by 1 millimeter every 10 million years because of the expansion of the universe.
Wow.
So you have to wait a while. You have to be very patient. To put that into context with gravity, if your hands were just 1 meter apart and you just let them come together because they're gravitationally attracted to one another, it would take them 2 days to come together and collide. So we've got 10 million years for the expansion of the universe over a 1 millimeter over 1 meter scale. And we've got 2 days for the collapse of your hands together because of gravity. So the theory is that gravity should take over, right? And everything should collapse down before the universe expands too much. Right? But it turns out that the universe expanded fast enough for that kind of large-scale gravitational collapse not to be able to occur. So this is why the prediction is that the universe is not going to collapse. And the opposite of a Big Bang is a big crunch. So they call it a big crunch. Yeah. The only other model, aside from the universe expanding and getting faster and faster and faster with its expansion and heading towards essentially zero energy per unit volume, and then it is that the universe gets to some point and then stops and is static. But that's such a fine. You need such a fine balance of forces in the universe that that's not what we think is going to happen. Yeah. Yeah.
Okay.
Yeah.
So what are some common misunderstandings?
Well, the common misunderstandings are understandings that are common to any scientific theory, right? So the misuse of the word theory in everyday speak. When we mean theory, we mean that it is the best explanation that we have for a particular question. All right. So how has the universe evolved? We explain that with the Big Bang theory. And theory in science is something very, very concrete. It's you might as well say fact rather than else. It's just some theory.
Right, it has quite a bit of evidence to back it up.
Yeah, yeah.
It's
overwhelming.
One guy.
Yeah. I mean, I wouldn't say that there is as much evidence as some other theories that we have. I mean, there are still details that we are working out. But yeah, I mean, it's the best model that we have. There is no model that explains it in any stronger way. Yeah, there's nothing that beats it. Okay. And if there was something that beat it, then that would be the theory that we'd be using, right? We would change our minds based on the evidence.
Right.
Yeah.
So Steve Hayes asks, and this goes along with Amanda's question, how can I relay all of this amazing information about the Big Bang, stars, planets, planet formation, etc., to my kids? Are there any experiments or ways that I can make it easier for them to understand?
Okay. So you can actually figure out what you can actually buy a radio that you can tune in and listen to the Big Bang. So you can tune a radio to a particular frequency and you can actually hear the hiss of the Big Bang.
Oh, that's cool.
You need about 1 millimeter. You need a microwave receiver to listen to it. I can't remember the wavelength off the top of it. It's something like 1.06 millimeters or something. You have to put that into hertz for a radio, but you can actually listen to it. And you can do a calculation. When you used to be able to tune your televisions between the stations, there would be some percentage of that white noise that would actually be the noise left over from the Big Bang. So you can buy off-the-shelf devices that can actually detect the radiation left over from the Big Bang. Yeah. But there's another couple of neat ways of explaining the universe to a kid using a balloon, for example. So the analogy that we used for a two-dimensional being living on a three-dimensional surface, in an expanding surface, you can use a balloon to explain that. So what you do is you blow up a balloon. You don't tie a knot in it. You blow up a balloon and then just put a whole bunch of dots with a marker all over the balloon, right? And then you measure the distance between those dots. And then you can either blow the balloon up more, and you'll see that the distance between the dots increases, or you can let air out of the balloon, and you'll see that the distance between the dots decreases. And that's the model that you can use to show in a three-dimensional way how a four-dimensional object like the universe is behaving. So that's another cool way. So balloons and radios and, kind of fun.
Yeah, that's awesome.
Yeah.
There's a couple of good books too, and I've mentioned this before. My daughter really loves the Big Bang Theory and talking about black holes, and so we have some of those books, and I'll dig those out and post information about those on the Godless Family website as well.
Excellent.
Let's see here. There was an announcement of the detection of gravity wave signatures in CMB a while ago, but now it seems there is doubt about it. What's the story there?
Okay, so one thing that has to happen early in the universe is there is a period that we call inflation, where the universe basically expanded by billions of orders of magnitude, so very, very quickly. And that's needed to explain, basically, how matter is currently distributed in the universe. So that period is known as inflation. And it's needed in order to reproduce the observations that we make today. But up until this point, there has been no observational test that has confirmed that this period of inflation occurred. Now, one of the consequences of having a universe expanding so quickly is it's kind of like the ringing of a bell. If you smack the side of a bell, the bell's going to vibrate, and that's the vibrations that you hear. So if you expand the universe really, really quickly, you're going to create vibrations through the universe that are actually compressions and contractions of space itself. So that's what we call gravitational waves. And you've got to be careful not to call them gravity waves. There's something that's a cloud formation. You've got to be careful to distinguish between the two. So gravitational waves are where you have a compression and stretch of a particular volume of space because space is being compressed and stretched by some really energetic event. So the signature of inflation should be this kind of ringing of a bell, which means that in the cosmic microwave background, which is that hiss that was heard, well, hiss that was detected in that horn antenna in New Jersey, there are actually slight fluctuations in that hiss, just like there are when you watch an explosion. There's kind of ripples on the surface of the explosion, right? Some part of that explosion is getting colder faster than other parts of that explosion. So that means there are ripples when you really, really look closely at the cosmic microwave background. Now, if you look even closer, you can actually see that the radiation that's coming from those ripples has got a slightly different orientation. We call that polarization. So that's how your sunglasses work. Your sunglasses work, if you have Polaroid sunglasses, your sunglasses work by only allowing through a particular orientation of light. So if you hold up your fingers, for example, and put them really close together, you would only see radiation that was orientated in one particular direction. Right? And you can test your you have Polaroid sunglasses by getting two of them and orientating them perpendicular to one another, and no light should come through. So if you're ever sunglass shopping, you can test that you have Polaroids by just getting two of them and rotating them. And if you can still see light coming through them, they're not Polaroids. Anyway, so if you have these ripples going on in the cosmic microwave background, and they're due to inflation, they're due to the kind of the ringing of the bell as the universe expanded due to inflation, then some of the light is going to be orientated slightly differently because the area of space it was coming from has got a slightly different compression and stretch than another part of the universe. So that actually puts a signal in the orientation of the radiation that comes from the Big Bang. Now, this experiment that was done was looking at the orientation of the radiation that was coming from the Big Bang, and it was called BICEP 2, and I can't remember what obviously it came after BICEP 1, but I can't remember what BICEP is for. But anyway, it was this experiment, and they needed to do it in a very isolated environment where there was no chance of there being any disturbance from sources that they weren't looking for. And when they got the results, they were consistent with what we would expect from the period of inflation and the gravitation and the signature of gravitational waves that would have been left in the cosmic microwave background. So it's not that gravitational waves were detected, it was a signal that is consistent with what we would expect gravitational waves to leave behind if they had occurred. Now, there's only been one observation of this, and it hasn't yet been confirmed. It's a fairly, according to the authors, it's a fairly strong detection, but there are currently, when this happens in science, rather than everyone getting a pat on the back, everyone else goes, right, let's see if they're wrong. And we're going through the let's see if they're wrong. phase of this detection right now. So it looks good, but it's being tested. If it's confirmed, then by an independent source, then we'll like it a bit more. There are some competing theories to do with dust and other things that could have affected the light as it traveled, that could have affected the signal from the Big Bang as it traveled towards us. But we'll leave it up in the air right now. It's a nice result, and everyone's kind of excited because it's the first kind of evidence to show that A, of inflation occurred, and B, that gravitational waves exist. So that's kind of why it was a big deal. Yeah, and it's staying in the news because of all of the people trying to explain it another way. Yeah, which is fine, which is encouraged, right?
Mm-hmm, mm-hmm.
Yeah, and there's still different explanations for gravity as well, right, going around. But
wow. Okay.
and the shape of the Earth, right? Some people still think the Earth's flat, right?
So Steve asked this question, and it was on our list of questions to ask you anyway. So I think now is a good time. What are some common arguments you hear from creationists who object or reject the Big Bang?
Can I ask one? I have one that
Sure.
I hear. Dan, how can something come from nothing?
Oh.
Okay.
That's
that. So it's on my reading list. Lawrence Krauss's book is on my reading list. I haven't got around to it yet. But basically, the universe, you can think of basically the universe as positives and negatives. So when you add it all together, it comes to zero, right? So if you take matter and antimatter and add it together, they both annihilate one another, and nothing happens, all right? So when we look really closely at things, we know that there are certain fluctuations that can occur simply because of the way matter is, right, or matter has to be. So if you consider how we detect things, we basically detect things by having light bounce off of them, right? So if you're seeing your hand, right, you're detecting your hand because light is bouncing off your hand back into your eye, and you see your hand, right? But light is little packets of energy that's bouncing off of the little molecules in your hand and coming back to you. Now, if you just consider a really tiny particle, and you try and detect that particle by bouncing light off of that particle, it's kind of like two billiard balls hitting one another. The photon is hitting another particle, and in the process of determining where that particle is, it actually alters where the particle is. Does that make sense?
Yes.
Mm-hmm.
Yeah. So there's this fundamental limit with how well we actually can know the position of something. Now we actually call that an uncertainty, and Heisenberg was the guy that came up with the explanation for it, so we call that Heisenberg's uncertainty principle. And that actually corresponds to a particular size of object, right? And then anything smaller than that, there are fluctuations that can occur that sum to zero within that size, right? But at any particular moment in time, you can have two particular things within that volume that, when you put them together, would cancel to zero, but right now they are not zero. So we call these kind of virtual particles. When you sum them together, they would make zero, but for a brief moment, they can be separate things, and then they would come back together, right? And this is actually one of the explanations for what's known as Hawking radiation. If you have that happen close to a black hole, you can have these virtual particles created. One of the virtual particles could fall into the black hole, and one of the virtual particles could move away from the black hole. So if you consider things like that, then when you look at things on very tiny quantum scales, then you can actually get fluctuations on quantum scales that essentially sum to nothing, but at that particular time they are something. Right? So if you had some kind of quantum fluctuation early in the universe, it could just be that we are one of these leftover fluctuations. Now, this is completely outside of my area of expertise, right? I could quite happily explain the Big Bang theory up to what's known as 10 to the minus 11 seconds, right? So 100 billionth of a second after the event occurred. So before that, it's more difficult to describe what happened, but people have done it. And one of the something from nothing arguments involves these quantum fluctuations. And if you speak to me again in a year, when I've probably got around to reading Lawrence Krauss's book, maybe I'll have a better explanation for you.
I heard somewhere that the beginning of the universe was pure energy. This was one explanation that I had heard. And because E equals mc squared, if you have the right mix, then energy could then create matter. That's one explanation I heard. What do you think about that?
Okay, so yeah, we're used to dealing with matter, right? We like picking things up and throwing them and moving them around. So we're used to dealing with matter in terms of electrons, neutrons, and protons, right? But if you actually put those things at very, very high energies, they break down into smaller and smaller and smaller components. And there comes a point, basically, where the whole universe is kind of a soup of these really fundamental particles. You may have heard of quarks before, right? Mm-hmm. So there's a point where the universe has got so much energy per unit volume that everything within the universe is not yet in the type of state that we experience the universe in. So protons have not yet formed, neutrons have not yet formed, and everything's really high energy, basically photons firing around and bouncing off of one another. So you can say that in the early universe, yes, it was not necessarily pure energy, but mostly energy, because the normal matter, the everyday matter that we experience, had not yet been formed. It took about a second for that material to form. Yeah,
that's amazing.
Yeah. Yeah. So it goes back to the ice analogy, right? The temperature scale is opposite in the universe. So the hot universe is really dense and compact, like ice. And as it gets cooler, it changes its state into this kind of liquid. And then we're in such a cool phase of the universe right now. It's all gaseous, right? And gas and light can travel through the universe, which is very useful if you want to see things. And yeah, so we've gone through these kind of phase changes in the universe, and these can actually happen with forces as well. So you probably know that electricity and magnetism are part and parcel of the same thing, right? Mm-hmm. But that wasn't originally known, and it turns out that at the current energies of the universe, electricity and magnetism are actually part of the same theory, right? So we can explain them using a set of 4 equations. We can explain electricity and magnetism using Maxwell's equations, right? But if you actually increase the energy of the universe, so you actually compact the universe into a small region, we actually predicted that other forces would actually combine into one force. So we have the electromagnetic force, and there's another force known as the weak force, which is a nuclear force that's responsible for carrying something that's known as gauge bosons, I think. But this is now the realm of particle physics, which is also kind of outside my area of expertise. But one of the things that the Large Hadron Collider was doing was proving that at high enough energies, you actually get a coupling of these fundamental forces. In fact, it wasn't even the Large Hadron Collider. I think it was done before that at a lower energy particle collider. There was a prediction that these two forces would come together, the electromagnetic force and the weak force. And as a result of those forces combining, we would detect these new particles. Hey presto, when we created that energy, these new particles were detected. So we know that there's this kind of phase transition in the fundamental forces in the universe. And at some energy, we think that the electro-weak force will combine with the strong force, which is basically the force that stops protons pinging apart in the center of an atom. And then we think at some point that would also couple with gravity as well. Then we would have a grand unified theory of everything. Mm-hmm. So there'd be a set of equations that would be able to explain everything that we see in the universe. You know, and that's the aim of you know, quite a few scientists to be able to do that. Yeah, so you can think of the universe as the early universe as going through these phase changes, of changing from a solid to a liquid to a gas almost. But the phase changes are actually fundamental forces, gravity and what keeps atoms together, things like that. Yeah. I can't even remember what the question was now. I had intended to write them down, but
no, I think you answered it. Did you get your answer, Amanda?
Yes.
Okay.
I did.
So back to Steve's question, what are some of the common arguments you hear from creationists or those who reject the Big Bang?
Well, the one's already been presented by Amanda. That's how do you get something from nothing? Mm-hmm. You know, you can wave your hand in a way to explain that. But it's important to remember that these are kind of very early points of the universe. We're talking about hundreds, billionths of seconds, right? So you frequently hear people talking about how the unknown is kind of this receding pocket of ignorance, right? We can explain everything up to 100 billionth of a second after the Big Bang. So, you know, before that, what's your problem? You've got this problem with 100 billionth of a second after the. Okay, all right, whatever. That's where their arguments lie. Everything after that we can explain. So that's what the something from nothing argument is one of them. The creationists kind of stick with the young Earth type arguments, right? Which really cosmology. You know, cosmology is way before then. So I don't really specifically hear any other arguments apart from the how do you get something from nothing. Yeah.
The only other thing I've heard is, well, if the Big Bang is true, then obviously God started it. That's the other thing I've heard. Sure.
But you know, it's if you use that argument, you might as well just give up. Right. If that argument was viable, we wouldn't know anything about the universe. We would have just said, "Great, we're done."
And I've heard people say that the young Earth creationists that the carbon dating and things like that, it looks like that because God created it to look like it was a lot older than it actually is, which I think is so interesting to me that like God would care about making it look older than it actually is. It's just,
God cares about you so much that he's purposefully tricking you.
Yeah, exactly.
Yeah.
I also hear I'm so sorry, I don't mean to interrupt, but that we already answered it already about you know, that it's just a theory. So that's definitely a big one as well.
Yeah. Dawkins liked to say, if gravity's just a theory, then jump out of a fourth floor window or something like that.
Exactly.
Which I wouldn't encourage anybody to do, by the way. So. Yeah. But going back to the carbon dating thing now, so what it really is radiometric dating. It's not carbon dating. So when you use carbon to date something, then you do have a limit. You do have an uncertainty associated with that. That means by the time you get to something that's about 6,000 years old, it does become highly uncertain. All right, because the half-life of a particular isotope of carbon-14, is about 6,000 years. But to age the Earth, we don't use carbon, we use uranium, which has a 4.5 billion year half-life. So when somebody says carbon dating doesn't work to date the age of the universe, to date the age of the Earth, they're right. But we're not using carbon dating, we're using radiometric dating, and we're using uranium, not carbon. So the evidence for an old Earth comes from radiometric dating, and people need to be corrected when they're using the kind of common term of carbon dating. We don't use carbon.
Okay.
Yeah. It seems to me the more I kind of dig into these theories that, you know, a year ago, 2 years ago, I feel like I knew a lot about. I believed that they were indeed fact. That the Big Bang is fact, evolution is fact. But the more I dig into them, the more I realize that we are really failing in educating our youth on these theories, because they're so interesting and they explain so much. And even just with the predictability part, I find that fascinating. And why wouldn't you want to teach young people to go out and make these kind of amazing predictions just based on just a theory? It bothers me that that we're falling short as a society.
Well, I think that there's 2 points that immediately come to mind. One is that it's not through lack of trying. right? I mean, there is an attack on intellectualism that's ongoing, right, coming from the conservative Christians, right? So so that it's not that we're not trying, it's just that our efforts are being eroded purposefully. There are people purposefully trying to undermine the education of children. So it's not as if we're not trying, right?
Right.
Second, these things are not easy. I mean, it's quite, you need, if you want to understand the details, you do need quite a lot of fairly high-level mathematics, physics, in terms of explaining the Big Bang, or in terms of explaining the evolution of a star, for example. And it's not really something you can turn around and easily and satisfactorily explain to, say, an 8-year-old.
But my thing is, just to kind of dig into that a little bit, I actually was looking up the evolution of a star just recently, actually, and simple things I didn't even know. There are 2 different sequences that a star can take depending on its mass. I mean, I knew that stars, depending on their mass, had different deaths, but just even understanding that it's a whole different sequence that their lifespan, I guess, takes. That's very simple. And how could I go through AP Physics in high school not knowing that?
Well, I mean, there are certain aims of AP Physics, right? And that's basically to get you not to get you to understand that what we call the post-main sequence evolution of a particular massive star, but to get you to understand why, for example, things don't move on your desk when you're not pushing them. Right. I mean, this is where physics should start, right? Just asking very simple questions, right?
Yes, and we did learn that. So.
Yeah. So. These are just simple questions that you can ask just for fun, right? Is get a child to explain why something doesn't move until you push it, and things like that. Because we have to start with our college students with that question sometimes in Physics 1, and it's very disappointing. I mean, obviously you always get a range of abilities of students, right? There's always going to be those students that you can't hold back and they're just really thirsty for more. But there are other students who are just sitting there waiting for you to tell them the answer. They're expecting you as the instructor to deliver their education to them, rather than them to actually work and understand and critically think about these types of problems. So yeah, just going around every day and asking why. I mean, it must be so fun being 8 again. Just asking why all the time. You just hope that, you know.
It is fun.
I hope that I have the answers when my children get to that age. But I love the question why. It's the best question there is.
My 8-year-old is so much fun because when she grows up, she wants to be a pet groomer. But in her spare time, she's going to be an astronomer.
You could probably reverse the priorities.
Well, that's the funny part. She's like, well, what kind of college do I need to be a pet groomer? And I'm like, honey, you don't need any college.
Give her a brush.
Depending on how deep you want to go, you might want to, learn some biology, some veterinary science. But to be an astronomer.
Yeah.
That would be a really expensive hobby and time-consuming.
So I think this is important, actually, when you're watching children grow up, is actually find what they're passionate about, find what they enjoy, and not try and direct their passions away from what they want to do themselves. So I mean, if my daughter's not interested in ballet, there's no way that I'm going to force her to do ballet just because she's a girl. She can do whatever she wants, as far as I'm concerned. If she wants to be a race car driver, then all power to her, because that would be her passion, her talent, and that's how she would go through life being happy.
I agree. I tell her if she wants to be a pet groomer, that's fine with me. I don't. Whatever she wants, and she knows that, and so it's kind of fun. And the other part is arguing with her about things. Like I remember she was misinformed, or she misunderstood something in class one day, and she was alliterating, and just for I don't know if everyone listening knows what alliteration is, but it's when words start with the same sound, like book, banana, barn. And so she was alliterating, and she said, "Mom, that's onomatopoeia." I said, "No, that's alliteration." She goes, "No, my teacher said that was onomatopoeia." I'm like, "Well, onomatopoeia are words that, describe a sound, like bang and boom and clank." And the argument I got from her, because all because she misunderstood something in class, and I actually kind of like that about her, because we had a whole conversation about it, and it's starting to seep into kind of the science stuff too. So we start talking about black holes, for example, which is your field of expertise. And she is a little misinformed about black holes. She thinks that they can actually come toward you. And I keep explaining to her, no, it's gravity. You would be going towards it. And you would know about it well in advance, probably billions of years in advance, so you're not going to have to flee. If you did. She doesn't believe me.
This actually highlights the attitude of a lot of people, and why they are not going to be convinced to change their mind about something that they believe. Right? They're stubborn, and no matter how much evidence that you'll produce to them, they won't change their mind no matter what, because there would kind of be an admission of defeat. Right? Nobody likes to be a loser. Right? I remember quite vividly thinking that the word vivid meant vague until I was about 14 years old, and I was absolutely convinced of it until I got out a dictionary, and I was like, oh, why didn't I do that earlier? It's a very important lesson, right? If you don't assume that what you think is right, go and make sure that it's right. And there's a big difference there between that way of thinking. I think that got me through. That got me through college. That got me, into the type of sciences. Is making sure that, just because I think something is a particular way doesn't mean that it is. Let's make sure that you understand exactly what's going on, and that it's the best explanation out there. Yeah.
Yeah, I think it's great that we're just even having that conversation. That she's asking questions and she wants to learn more.
Yeah.
And then we go explore together and.
Right. Yeah. So yeah, the answer to the next response after I don't know is let's find out.
Yeah.
Yeah.
Definitely.
Great.
So do you have time for one more question?
Oh, absolutely. Yeah.
So is it Kira or Kyra?
Kyra.
Kyra, thank you. What are your thoughts on the recently discovered mega-Earth exoplanet Kepler-10c and how it affects the previously held theory regarding gas giants versus smaller terrestrial planets? Do you want to take that? Thought you might be interested in it.
Yeah. So. So if I skimmed that article, I skimmed one of the articles about it. So I think that planet is actually going to be too close to its star to be able to successfully harbor life. I think it's going to be too hot. I mean, it's kind of interesting that you can have a planet, a rocky planet, a kind of planet like the Earth, which we call terrestrial planets, be only twice the diameter but be 17 times the mass. Right. Now you have to be careful with comparing something that's twice the diameter, because when you actually look at the volume, when you compare the volumes and then the total mass, it actually goes as the cube, right? Because the volume of a sphere is 4/3 pi r cubed, right? So if you double the radius of something, you don't double its mass. The mass goes up by loads, right? But anyway, it looks like that planet is more massive than the Earth, and so we think that the actual core of that particular planet, Kepler-10c, is going to be a lot more dense than the core of our own planet, the iron core of our own planet. And then you can consider, the importances of having an iron core and kind of a liquid magma, because it allows you to, as the iron core spins, it actually generates the magnetic field that's protecting us from a lot of the harmful radiation that's coming from our own sun. Right? So if you're considering whether or not there could be life on another planet, one of the things you may well need is a magnetic field on that planet to help shield any of the life from harmful radiation. That being said, there may be a particular form of life evolve on that planet that is, completely capable of existing in the face of that radiation.
Mm-hmm.
So the exciting thing with finding all these planets is this is a new thing, right? 20 years ago, we didn't know of any planets outside of our own solar system. Today, we know that any star that you look at in the night sky is going to have a planet around it. In fact, the observations that we've gained over the last 5 years show that there's more planets in the universe than there are stars.
Oh, wow.
My goodness.
Awesome.
Yeah.
Definitely.
So my Star Trek fantasy might come true, 500, 600 years from now, where we're roaming through the galaxy with the Vulcans and.
Well, I think in the Star Trek universe, we're only 200 years away from first contact, right?
Oh yeah, yeah. I gotta get myself cryogenically frozen so I can be around for that.
Oh yeah, you can do that. You'll be fine. Yeah.
So our hour is up. Is there anything else that we want to talk about? Anything that I missed?
Probably.
I'll think about 10 questions in the next half hour, but nothing that I can think of right now.
That's how it always goes.
Yeah.
Yeah.
Okay. Well, hopefully we can still get in touch with you, Dan, after the show if we have more questions.
Yep. Yeah, absolutely.
I can barrage Dan with questions.
Go right ahead.
Well, thank you so much for coming on. Before we go, I always give our guests and Amanda an opportunity to promote anything. Is there anything you'd like to promote?
Oh, me?
Yeah, anything.
If you would like to enroll at my university, that'd be awesome.
Well, you might see Aura there someday.
Sounds good. Yeah, sounds good.
She's got a thirst for knowledge. You can't stop her, and why would I want to?
Right, and we've got the Space Center just up the road. So rockets are always cool. Yeah,
yeah, totally. I imagine my children someday being like Sue and Johnny Storm. They have these same personalities, where Sue Storm and Aura, the very measured scientist, very serious, and my son and Johnny Storm are like, woohoo, let's have an adventure, and I'm gonna go fly this rocket. We were watching Star Trek today, and the Into Darkness, and there's the beginning where Kirk and McCoy jump off the cliff into the water to swim down to the Enterprise, and my son's like, that looks like fun. That's like a 60-foot cliff, dude. What are you talking about? So yeah, that's how I imagine they will be. I kind of hope.
Yeah.
Amanda, anything that you want to promote?
Yep, ProfitCast. My husband's podcast. I would say me and my husband's, but maybe that would be taking too much ownership over it. That's on Sundays at 9:30 Pacific time. Yeah, but I think you should talk more about your subscriptions because I think that's really exciting.
Yep, definitely. I have started the subscription portion of my website, or of the Godless Family website. And so right now, what's on there are the take and teach lesson plans that I've developed, and the whole point of the lesson plans is to give parents or groups, if groups want to get together, something that's completely downloadable and essentially not have to get much outside of that lesson plan in order to teach your children or talk to your children about some of the ideas presented. And then if there is anything else you need to get external, there's a list of materials. And it covers all kinds of things. It covers evolution, it covers Big Bang, it covers morality, mortality. I even did a sex education one because my children know so much about procreation, just because they're so interested in animals and watching Discovery. The questions are coming, and so if parents are in a similar situation, then there's resources there for them to kind of sit down and have that chat with their children. So that's all there. It is pay to subscribe, just because it is very time consuming. But right now it's not much. Right now I'm running a promotion where 6-month subscription is $5 and a year is $10. So I'll post a link to that for anyone who's interested, and I'll be building more to that, to adding more as the summer goes on and as I have time.
What would you say the age ranges are on there?
I have it divided up between elementary, middle, and high school. And the high school is completely free. And what I did for high school is just ideas, things that I know other groups have done. So high school students, I figure by the time your children get to high school, you've already talked to them about these things. That's the assumption.
Hopefully.
And that they're out kind of doing their own exploring. And so there's just kind of, those are just ideas for students. And I'm thinking groups like Secular Student Alliance groups and or just friends that want to get together and do something. And then there's middle and elementary. And then you have to adjust the lessons based on the abilities of the children, of course. A student who's maybe in 5th grade, you might want to move, look at the middle school lessons and so on. So there are free lessons for you to browse too. So you can kind of get an idea of what they're like without having to get the subscription too. So that's my big promotion, that's my big announcement, and I'll post a link to that. And I want to thank Dan for coming on the show, and hopefully we'll get him back again someday.
Sounds good. Yeah.
Yay.
And I think that's it today. So I will say good night to everyone, and see you next week when we talk about fundamental Christianity. Bye.